Hello, welcome back. I'm John, an old YouTuber. It's soon 12 noon. I got up late after 9 a.m. So let's get started to do something. So just to upload a video. So let's do my computer ready. So I did put my computer to sleep tonight, but I cannot keep do that like 10 days because I have to reboot my computer. But I have so many PDF open. I like to read about the oldest Intel CPUs. But I have to I like to read about this three-dimensional integrated circuits. But let's. I don't think we have power enough. Yes. But we need one more. This international technology roadmap for semiconductors, but that's a short one. Then I like to read about all these old Intel CPUs, the oldest. All this 8088. That's the first, like the first generation. 8086 and 8088. That was the CPU was inside the first IBM PC. And the 8186. And this one famous 8286, but that's from the old day, from the PCs in old days. I like to read about it again. And the 380, 386 and the 4. But before that I need to finish this. So I will go back to my bed. I will check my cell phone. Yes, I need a minute to do myself ready. But Intel had pronounced around the year 2013, in only 7 years, they will make like 10 trillions of transistors. Today they have billions. Today they have few billions on the GeForce graphic card. They should have like 47 billions of transistors, but somehow they will go to many thousand of billions. They will make the number of transistors inside these CPUs from many billions to many trillions. Trillions, 1,000 billions and 1 trillion. So they are talking about 10 trillions in just 7 years. It could be something about that. Three-dimensional. But 7 years is not so long time, because they need to build some factories can do it. So I don't believe it. I don't believe it's possible to make a small CPU chips with 10,000 billions. Yes, I have a Danish video I will put public. No, I don't believe that you can make this small computer chips with 10,000 billions transistors in just 7 years. And today they have less 10 billions, from 10 billions to 10,000 billions in 7 years. I don't believe that. But of course, every generation of new Intel CPUs will have more higher number of transistors, but not from 5 billions to 10,000 billions in 7 years. I don't believe it, but maybe Intel, they are researching. They know more about this technology than I do. I'm just an old man on a pension. Probably Intel, they know more about this than I do. Intel, they have some research labs. I think they have some very clever researchers, computer engineers, and they are spending billions of dollars to research in future CPU technology. They have some research labs, but let's read about it.
Three-dimensional integrated circuit. A three-dimensional integrated circuit, 3D IC, is a MOS, metal oxide semiconductor, integrated circuit, IC, manufactured by stacking silicon wafers or dies and interconnecting them vertically using, for instance through silicon vias, TSVs, or CU-CU connections, so that they behave as a single device to achieve performance improvements at reduced power and smaller footprint than conventional two-dimensional processes. The 3D IC is one of several 3D integration schemes that exploit the Z direction to achieve electrical performance benefits in microelectronics and nanoelectronics. 3D integrated circuits can be classified by their level of interconnect hierarchy at the global, package, intermediate, bond pad, and local, transistor, level. 1. In general, 3D integration is a broad term that includes such technologies as 3D wafer-level packaging, 3D WLP, 2.5D and 3D interposer-based integration, 3D stacked ICS, 3D. 6. Monolithic 3D ICS, 3D heterogeneous integration, and 3D systems integration. 2. 3. International organizations such as the GISO Technology Roadmap Committee, JIC, and the International Technology Roadmap for Semiconductors, ITRS, have worked to classify the various 3D integration technologies to further the establishment of standards and roadmaps of 3D integration. 4. As of the 2010s, 3D ICS are widely used for NAND flash memory and in mobile devices. Contents. Types 3D ICS versus 3D packaging. 3D6. Monolithic 3D ICS. Manufacturing technologies for 3D6. Benefits. Challenges. Design styles. History demonstrations, 1983-2012, Japan, 1983-2005. Europe, 1988-2005. United States, 1999-2012. Commercial 3D ICS, 2004 present. See also. Notes. References. Further reading. External links. Types. 3D ICS versus 3D packaging. 3D packaging refers to 3D integration schemes that rely on traditional interconnection methods such as wire bonding and flip chip to achieve vertical stacking. 3D packaging can be divided into 3D system in package, 3D SIP, and 3D wafer level package, 3D WLP. 3D SIPs that have been in mainstream manufacturing for some time and have a well-established infrastructure include stacked memory disinterconnected with wire bonds and package-on-package, POP, configurations interconnected with wire bonds or flip chip technology. POP is used for vertically integrating disparate technologies. 3D WLP uses wafer-level processes such as redistribution layers, RDLs, and wafer bumping processes to form interconnects. 2.5D interposer is a 3D WLP that interconnects dies side by side on a silicon, glass, or organic interposer using through-silicon vias, TSVs, and an RDL. In all types of 3D packaging, chips in the package communicate using off-chip signaling, much as if they were mounted in separate packages on a normal circuit board. 3D ICS can be divided into 3D stacked ICS, 3D SIC, which refers to stacking IC chips using TSV interconnects, and monolithic 3D ICS, which use fab processes to realize 3D interconnects at the local levels of the on-chip wiring hierarchy as set forth by the ITRS. This results in direct vertical interconnects between device layers. The first examples of a monolithic approach are seen in Samsung's 3D VNAND devices. 5. As of the 2010s, 3D IC packages are widely used for NAND flash memory in mobile devices. 6. 1 master die and 3 slave dies. 3D 6. The digital electronics market requires a higher density semiconductor memory chip to cater to recently released CPU components, and the multiple die stacking technique has been suggested as a solution to this problem. JEDEC disclosed the upcoming DRAM technology includes the 3D SIC die stacking plan at Server Memory Forum, November 1, 2011, Santa Clara, CA. In August 2014, Samsung Electronics started producing 64 GB DRAM modules for servers based on emerging DDR4, double data rate 4, memory using 3D TSV package technology. 7. Newer proposed standards for 3D stacked DRAM include WiDi/O, WiDi/O2, hybrid memory cube, high bandwidth memory. Monolithic 3D ICS. Monolithic 3D ICS are built in layers on a single semiconductor wafer, which is then diced into 3D ICS. There is only one substrate, hence no need for lining, thinning, bonding, or through silicon vias. Process temperature limitations are addressed by partitioning the transistor fabrication into 2 phases. A high temperature phase which is done before layer transfer followed by a layer transfer using ion cut, also known as layer transfer, which has been used to produce silicon on insulator, SOI, wafers for the past 2 decades. Multiple thin, 10s 100s nanometer scale, layers of virtually defect-free silicon can be created by utilizing low temperature, and LT400, bond and cleave techniques, and placed on top of active transistor circuitry. Followed by phenolizing the transistors using etch and deposition processes. This monolithic 3D IC technology has been researched at Stanford University under a DARPA-sponsored grant. CEA-Leti is also developing monolithic 3D IC approaches, called sequential 3D IC. In 2014, the French Research Institute introduced its Cool Cube trademark symbol, a low-temperature process flow that provides a true path to 3Z.8. At Stanford University, researchers are designing monolithic 3D ICS using carbon nanotube, CNT, structures versus silicon using a wafer-scale low-temperature CNT transfer processes that can be done at 120.9. In general, monolithic 3D ICS are still a developing technology and are considered by most to be several years away from production. Manufacturing technologies for 3D 6. There are several methods for 3D IC design, including recrystallization and wafer bonding methods. There are two major types of wafer bonding: CU-CU connections, copper-to-copper connections between stack discs, used in TSVs 10, 11, and through silicon via TSV. As of 2014, a number of memory products such as high bandwidth memory, HBM, and the hybrid memory cube have been launched that implement 3D IC stacking with TSVs. There are a number of key stacking approaches being implemented and explored. These include die-to-die, die-to-wafer, and wafer-to-wafer. Die-to-die electronic components are built on multiple die, which are then aligned and bonded. Thinning and TSV creation may be done before or after bonding. One advantage of die-to-die is that each component die can be tested first, so that one bad die does not ruin an entire stack. 12. Moreover, each die in the 3D IC can be binned beforehand, so that they can be mixed and matched to optimize power consumption and performance. E.G. Matching multiple dies from the low power process corner for a mobile application. Die-to-wafer electronic components are built on two semiconductor wafers. One wafer is diced. These ingulated dice are aligned and bonded on two die sites of the second wafer. As in the wafer-on-wafer method, thinning and TSV creation are performed either before or after bonding. Additional die may be added to the stacks before dicing. 13. Wafer-to-wafer electronic components are built on two or more semiconductor wafers, which are thin-aligned, bonded, and diced into 3D ICs. Each wafer may be thinned before or after bonding. Vertical connections are either built into the wafers before bonding or else are created in the stack after bonding. These through-silicon vias, TSVs, pass through the silicon substrate, S, between active layers and / or between an active layer and an external bond pad. Wafer-to-wafer bonding can reduce yields, since if any one of N chips in a 3D IC are defective, the entire 3D IC will be defective. Moreover, the wafers must be the same size, but many exotic materials, for example 3VS, are manufactured on much smaller wafers than CMOS logic or DRAM, typically 300 mm, complicating heterogeneous integration. Benefits. While traditional CMOS scaling processes improve signal propagation speed, scaling from current manufacturing and chip design technologies is becoming more difficult and costly, in part because of power density constraints, and in part because interconnects do not become faster while transistors do. 14. 3D ICs address the scaling challenge by stacking 2D dies and connecting them in the third dimension. This promises to speed up communication between layered chips, compared to planar layout. 15. 3D ICs promise many significant benefits, including footprint. More functionality fits into a small space. This extends Moore's law and enables a new generation of tiny but powerful devices. Cost partitioning a large chip into multiple smaller dies with 3D stacking can improve the yield and reduce the fabrication cost if individual dies are tested separately. 16. 17. Heterogeneous integration circuit layers can be built with different processes, or even on different types of wafers. This means that components can be optimized to a much greater degree than if they were built together on a single wafer. Moreover, components with incompatible manufacturing can be combined in a single 3D IC. 18. 3. Shorter interconnect. The average wire length is reduced. Common figures reported by researchers are on the order of 10–15%, but this reduction mostly applies to longer interconnect, which may affect circuit delay by a greater amount. Given that 3D wires have much higher capacitance than conventional in-die wires, circuit delay may or may not improve. Power. Keeping a signal on chip can reduce its power consumption by 10–100 times. 19. Shorter wires also reduce power consumption by producing less parasitic capacitance. 20. Reducing the power budget leads to less heat generation, extended battery life, and lower cost of operation. Design. The vertical dimension adds a higher order of connectivity